All right, hello everyone. I'm Henry. Today I'll be instructing the seminar. I'm a PhD in the CSCE department, and today I'm excited to welcome Dr. Peng for our seminar class today. He's an assistant professor in the computer science and engineering department here, and previously he was a postdoctoral researcher at the University of Canada. He obtained his PhD degree from University of Iowa. His research interests includes quantum programming languages, type theory, and theory applications. Today, we will be talking about designing quantum programming languages with types. With that, please take it away.
Thank you. Good afternoon, everyone. It's great to see you all here. We have a small crowd, which is nice, which means that I get to do a lot of things in this seminar. So yeah, today I'm going to talk about designing quantum programming languages with types. So the first question that one might ask is, why are we interested in quantum programming languages? Well, there are several reasons. I guess the most important reason is that over the year, quantum computing has been in a very fast development. Researchers from different areas, they identified that there are certain quantum algorithms that can solve problems that can offer substantial computing speed up compared to using conventional algorithms. So there are basically two major examples of that. The first one is the use of quantum algorithm to factor integers, which is a very fundamental part. It's often considered a fundamental hard problem in the areas of cryptography. So there are evidence that using the technique from quantum computing, one can vector integer in a very efficient way. And another area is about simulating of physical system or chemical system. There, researchers have also figured out that using quantum circuit, one can sort of find a faster algorithm to do physical simulation versus using conventional methods. So those are fairly exciting areas that quantum computing have shown evidence that it can offer substantial speed up. So that's on the algorithm side. On the hardware side, there are also advances by big companies like IBM and Google. They have actually made a quantum computer available. For example, in our department, we actually have ability to access IBM's quantum computer. So that's something. So those advances sort of make it possible to talk about what kind of program we want to run on a quantum computer and what can a quantum computer actually do, right? So that's a very important aspect when we talk about quantum programming languages. So in terms of quantum algorithm, in practice, researchers in the areas of quantum computing, when they talk about their algorithm, most likely they will talk about, we can use this circuits to do such and such. So what I want to say is that quantum circuit is like a de facto language for researchers to sort of communicate their idea in the research areas of quantum computing. So it becomes natural to consider to develop a programming language that allows us to program quantum circuits, right? So in that way, it becomes easier to integrate the fact of the act of programming into the quantum computing research. So in this talk, we will mostly focus on programming language that are for constructing quantum circuits. So, and of course, when researchers, when they are talking about quantum algorithms, they sort of express the idea at a fairly high level. They assume there are a lot of basic building blocks that are already presented, right? So what would be an example of that, right? For example, they might say something like, oh, to solve this particular problem, let's apply this circuit 100 times or 1,000 times, right? So, so what this means in terms of programming languages, right? We know, well, in programming languages, to iterate something 100 times, right? We can always use either like a for loop, while loop, or a recursion to do such thing. So, so it's essential that in the programming language level, we are able to sort of allow programmer to write things like that, like repeat a circuit that many times, or another example would be sometimes when researchers in quantum computing they come out with a circuit, they want to sort of perform certain operation on those circuits. One of the operation is like apply the control over the circuit. So what does that mean? It's like almost like a conditional. It's like, oh, if this condition is true, then you apply this quantum circuit. But when this condition is false, then you apply the identity operation. So that's what they call controlling a quantum circuit. So this is also like a fairly high-level operation. It's sort of assume you already have a quantum circuit, and then you just apply this control operation to the quantum circuit, then you get a new quantum circuit that does the same according to the conditional. So we want our high-level programming language to also support this kind of operation. And another reason that we are interested in quantum programming languages is about debugging quantum algorithm, right? So in the usual programming task, we often need to debug our program, right? So how do we debug our program? Well, we sort of do some printing of the value of the variable maybe in the middle of your program to see what's going on and so on, right? So in a sense, we are sort of setting some breakpoint so that the program sort of stops at that breakpoint, and then you look at the value for each variable to see what's going on. So that's what we normally do for conventional programs, to debug conventional programs. But for quantum programs, this kind of thing becomes almost impossible because it's actually the fact that we cannot simply just stop a quantum program, and even if we can, the fact that we are looking at the value of the variable, this is actually correspond to an operation that is called measurement in quantum computing. So what measurement does is that it actually changes the state of the system. So the fact that you are looking at the value of the variable, it actually changes the state of the quantum system. So this means that the conventional debugging technique becomes infeasible for quantum programs. So so we would like our programming language to sort of give programmer certain kind of guarantees before we are sending the program to the quantum computer to run, right? So before we even try to run the program, we would like to make sure that, oh, this quantum program actually will generate a circuit, right? Not just generating some random garbage. So for example, so this is something that a programming language can provide. So that's also the reason, in my opinion, that we are interested in designing a quantum programming language that supports this kind of thing. So one main technique that I use is it's called types. So the idea here is that we want to use types to make sure that the quantum circuit, are sort of connects in a correct way, so that in the end we get a correct quantum circuit, so that we can send the circuits to the quantum computer to run. Okay, so that's a fairly long explanation of why we are interested in quantum programming languages. But let me briefly talk about my research interest. Yeah, so I am interested in answering the following question, but in the areas of quantum computing, I'm mostly interested in building tools to facilitate programming quantum computer. So in this talk, we will focus on the question of how to design a high-level programming language for quantum circuits. And of course, in general, I'm also interested in verifying the correctness of the quantum programs, and also how do we run the high-level quantum programming language on actual quantum computer, and also what kind of algorithms we can run on the current quantum computer. So yeah, so I mentioned that the motivation of quantum programming language is, for me, is to provide some kind of guarantee for the quantum circuits before we send the circuits to the quantum computer. And the technique that I use is type. So why do I think type is a good way to ensure the well-formedness or the correctness of the circuit? Because, for example, we know that types are essentially like a lightweight specification of the program, right? When we look at any program, that's what I'm going to say. So examples of types are, right, in languages like Java or C++, you have types, I think, right? So when we look at the program, the first thing we sort of look at is what is the input type of this program, or what is the type that this program will return, right? What is the value that this program will return? So this is sort of like the types that I'm talking about, but I'll be more specific in a moment. But the idea here is that when we look at the type of the function or the program, we sort of already have a vague idea of what this function does, right? If this function takes two numbers as inputs and returns some number, we know it's doing something with the number, for example. We cannot just give a string to this function, for example. So types, in a way, sort of already give you some information about what the program does. And so in the context of my research, I also want to use types to enforce the so-called invariant. So the invariant, in this case, it will be the well-formedness of the circuits, which we'll see that in a moment. And also there's this slogans in the type theory community, which is a well-typed program should behave, should be well behaved, right? If your program passes the type checker, it should at least behave like like a reasonable program. So that's what this well-typed program satisfies certain properties mean. Okay, so that's fairly high level. But now let's look at a kind of an idealized programming language. So this will be idealized in the sense that it doesn't have a lot of features and things, but it does try to sort of provide an abstraction to like the program that we are familiar with. So in this idealized programming language, we have three kinds of programs, right? So a program can be a variable, which is that the x over there. And a program can also be a function. So this lambda x dot m is like a function that has input x and then output n as the output. And in our program, we can also supply an argument for a function, or it's also called sort of application, right? So the n followed by n. The intended meaning is that we are supplying the program n with an argument n. So these are only like three things we can do with our program. A program, right? So a program can either be a function, or we can supply an argument for a function, or we can, or it is a variable. So that's our program. So what are the types? Well, the types in this case are also fairly simple or idealized. So the types can be like a built-in type C there. So what would be built-in type? For example, like integers or number, booleans, and things like that. And we can also have function type like A arrow B. So that means that if we have a program that has the type A arrow B, that means that that program is expecting an input of type A, and then the output type of that program is B. Okay. So in this setting, we can talk about a typing environment. So what would be a typing environment? Well, it is basically a list of variables and their types. Okay. So that's what we call typing environment in this idealized language. So with that, we can then talk about when does a program has a type. So that's called typing judgment. So the gamma there is the typing environment. So it's saying that the program n has type A in the typing environment gamma, right? So then we will need a set of rules to determine when does a program n has the type A. So in that case, we will have three typing rules to determine the type of a program. So the first rule is fairly straightforward. The first rule says that a variable has type A, and that is true when the variable is already declared in the typing environment who already has type A, right? So that's the like the base case of this typing rule. And the second rule is more interesting. So the second rule says that when do we have a function type, or when do we have a program that has this function type A arrow B? Well, we have that if the program n has type B, but under this environment. So if in our typing judgment or typing environment, we have a variable x of type A, and then the program n has type B under that environment, then we say, oh, then this lambda x dot n program is a function, is expecting an input argument of type A and then output something of type B. Right? So that's how we determine a function can have a function type. So the lambda x dot m is really like a function that is expecting the x, lambda x there is like an argument of the function, and then the m is what the function will return. Okay. And then once we have a function type, then we can, right, there's only one thing we can do with the function, right? Namely to apply the function with the argument. So that's what the last rule is talking about, right? If we have a program N that has the type A arrow B, that means that if we supply this N with an argument N of type A, then we will have a new program that has type B. Okay, so that's like in this very idealized programming language, we can talk about what are the programs, what are the types, and when does the program have a type. Any questions so far about the typing rules here?
I think the typing rules are generally true, even in the current programming paradigm, but not necessarily. Has to be true in the content programming paradigm, right?
Yeah. So those typing rules are not only for quantum program, it's also for any classical program as well. So here we are really talking about idealized programming language here. So it is supposed to behave like for any kind of program. Okay. All right. So that's the typing rules. So in practice, of course, we don't want to manually check whether a program has certain type. So in practice, we want to program a tool which we call type checker, which will check whether whether the program N has type A. Right? That is also what in languages like C++ or Java or any kind of static type programming languages, they all have a component called type checker. Namely, if your program is not type checked, you wouldn't be able to compile your program. That's the type checker is the reason behind that. But it's a good thing because you want your program to return correctly before you compile your program. So this makes sense, at least to me anyway. So there's another component in the programming language, or for this idealized programming language, which is called evaluator. So what it does is that it tells us how to run the program, right? So if we have a program, of course we are interested in how to run this program and what this program will return, right? So that's what the evaluator is doing. So if we have a program called N, and then that N down arrow V means that we sort of use certain rules to evaluate the program N to a value, which we call V. So that's what the evaluator is doing. It's trying to evaluate the program and give us the value of that program. So those the type checker and the evaluator are the components of the programming languages in general. So when we talk about typing, one of the most important theoretical property, it's called type safety. So what does that mean? Well, it says that if we have a program N that has type A, and when we evaluate this program, we get some value, let's say the value is V, then that value better has the same type as N, right? If N denotes is doing some arithmetic and return a number, and we want that number we want the value to has the number type. So that's what we mean by type safety in this idealized setting. Any questions about these three remarks? If not, let's move on. So we talk about, so in the idealized programming language, we basically only have two kinds of type, right? We have the built-in type, which can be bool or integer or numbers. We also have function type, which denotes a function, input type, and output type. But in more advanced type series, people also come up with a lot of new fancy types that you might have not seen before, right? So one of those types is called a linear type, which is very relevant to quantum programming language that I will talk about later. But what does that mean? So we have we call that simple lollipop, A lollipop B, but it's called linear types. So what it means is that it's like a function type from A to B, but it's not any function. It's a function that sort of consumes the input A exactly once. Or in other words, this A lollipop B means that we are viewing the input A as some kind of a resource. Right? So what do I mean by resource? So resource here is like things that we cannot just duplicate, right? For example, like a physical things, like a chair is you cannot just like make another copy of the chair, but this might not be a good analogy. Or money, right? When you have $5, you have $5, right? You do not like make another copy of $5. Right. So that's what I mean by resource. It's something that once you use it, then it's gone, right? It does not come from nowhere and it does not disappear from nowhere. It's something that you have to obtain and you have to use. So that we'll see more example about that. But that's a kind of types that will be relevant in for quantum programming language. So there are another kind of types which is called dependent type. It's like so in this case we have an example. So here we have n:\math. So it means that we have a function here that is expecting a number as input. And then the second input is a vector of type A of length n. So it's like a list of elements of type A. So it's like a list where each element has type A, and that list has length n. So what that type is saying is that if you give that function a number, say 3, then we will get a new function that is vector A of 3, arrow vector A of 3. So we get a new function that is expecting an input of length 3, and then it will output a list of length 3. Right? So it's sort of parameterized by the first input, which is the natural number. Right? If we give a number 5, in that case, the function that we get is vector A of 5, arrow vector A of 5. So in that case, we have a new kind of function, but they only differ from the one by 3 by the number. Okay, so and of course there are also new possibility, like we might have types like A arrow alpha B. So it's also like a function type A arrow B, but maybe this function should also satisfy more properties. Like this function should denote the quantum circuit, for example. There would be another kind of type, right? So in research, there are many sort of this kind of fancy new weird types that you often see as when you're working on type theory for quantum programming languages. So now let's go back to the quantum programming language a bit. So what are the basic types that we can have for quantum computing? Well, the first basic type is called bit. So a bit should be familiar to everyone because it only has two possible values, 0 or 1. So that's straightforward. But in quantum computing, there's also this sort of new type or new object, which is called qubit. So a qubit is more complicated, right? It's like so how do we describe a qubit? Well, a qubit is actually a linear combination of 0 and 1, where by linear combination, I mean it's a sort of a formal sum of alpha times 0 plus beta times 1, where alpha and beta are complex numbers, and they are the square of the absolute values for alpha and beta, they add up to 1. So that's how mathematically we can describe the state of a qubit. So already here its qubit just seems so different from bit in the sense that for bit, a bit value can either be 0 or 1, whereas a qubit, the state of a qubit is actually sort of, some people say in some sense it's sort of both 0 and 1 at the same time with certain probability. So yeah, so that's qubit. Now, of course, in practice, we have many qubits, right? We are not just working on, for quantum programming languages, we are not just interested in working on one qubit. We might have like many qubits that we want to work with. So the way we express when we have like multiple qubits is by using this concept which we call tensor product. But what it means, what specifically it means, it's not important. But what it implies is that if we want to work with 2 qubits, then we might. So that means that we might want to work with a type that is of this form, like qubit is tensor product of another qubit. So that's how we work with 2 qubits. And then similarly for 3 qubits, 4 qubits, and so on.
I have a question with clarification. Why alpha and beta are complex numbers? Why just not having real numbers as the coefficients? Why is it? Can you give an intuition, or is that? I mean, maybe it's beyond the scope of it.
Yeah, I suppose this comes from physics. In some ways, I'm not a physicist, so I'm not really qualified to say that. But I think the reason might come from the fact that in physics, you want to work with complex number, and it gives you a lot of flexibility to express the evolution of a physical system that somehow can be better described by complex numbers versus real numbers. I suspect that's the reason. But yeah, but when you work with quantum computing more, you will realize that when you have complex number, it allows you to do more things in terms of computation as well. So that might be another reason that people use complex number.
I have one follow-up. So in some sense, bit is normally like a transistor or CMOS, right? One CMOS represents 1 bit. There you can. Is there any equivalency in the qubit, like I believe some sort of energy state, or like my question was like, let's say if I have 1 qubit, how much equivalent bit I can have? Like let's say 100 bit, I can represent in a qubit, or is this anyway
Right. Yeah. So already, if we just look at the form of a qubit, there are basically infinite possibilities, right? Because alpha and beta are complex number, and a complex number that's like uncountable. Yeah. I don't know if it's countable or uncountable, many of complex number, but yeah. So you were saying a single qubit can already sort of encode a lot of information. But then But then but in the end, the way we use qubit in quantum computing is that we want to measure qubit. So what measurement does is that it turns the qubit into bit. So it sort of collapses all the possibility into just like 0 or 1. So you lose information by measurement. Any other question? Right. So yeah, so that's the basic sort of types of objects that we work with in the quantum programming language. So I talked about resource a bit earlier, but here I want to sort of emphasize that qubits are sort of like a resource in our quantum programming languages. So what does that mean? Well, there's a slogan in quantum computing saying that it's called the so-called no cloning theorem or no cloning property. But essentially what it's saying is that we cannot duplicate a qubit. So if we have a qubit, we cannot easily sort of define a set of operations that sort of produce 2 copies of the same qubit. That's actually not possible.
Which programming language?
Oh, yeah, I haven't talked about that yet, but this doesn't really, it's not a programming language related concept. It's more like a quantum computing concept. We are talking about the stage of a qubit. In general, there's just, you cannot find a set of operations that allow you to duplicate the stage. But I'll talk about the programming language in a moment.
If I may make a comment, it looks like the first line is a type specification with a column, and the second one is you're giving an expression there, or
oh yeah, I should explain that. I haven't explained the. Are you referring to this?
No, I'm sorry. The unit.
Yeah.
This here is a function, and that is time.
Yeah. I'll explain that in a moment. Right now, I'm just explaining this. Yeah, I'll get to that. But
otherwise, I mean, f(x) equals xx. That could be written in Haskell, for example,
yeah.
Exactly as it is.
Yeah. So what this line means is that, for example, we might want to define a function called dup, for duplicate. It has an input x, but then its output is a pairs of things, right? We know we can do that when x is a natural number, for example, right? If we have x is a natural number, we can, at least at the programming language level, we can use that variable which has value number how many times as we like. But when that variable refers to a qubit, you better be careful about whether or not you're actually duplicating it.
Qubits are basically like spin of the electron and it stays. So why is it not duplicable if they can create the same?
Yeah, why can we not duplicate the qubit? That's a very good question. For the time being, I wouldn't be able to explain to you exactly why, but if you take a quantum computing class, I believe here Professor Steve Fenner is offering a quantum computing class. If you take that class, you'll understand why you actually cannot. But yeah, for the time being, I cannot explain this right now. But there are mathematical reasons that you actually cannot. So that's the surprising thing on this property. Okay, so that's no cloning property, right? That already is sort of a little unusual about quantum programming languages in some sense with time. Okay, so another point of qubits resource is that qubit does not exist in a vacuum. So what does that mean? Well, it means that if we want to use a qubit, we have to initialize a qubit and then we use it. So here this init 0, it's like a linear type, right? It takes a unit as input. So the unit is just like almost like void in class or a singleton So it's a type that has only one value, so it's like a dummy input. So and then it sort of return qubit. So that's like a initialization for a variable, if you will. So if we want to use a qubit, we better initialize, and then we can use it. Right? So that's what I mean by qubit does not exist in a vacuum. And then qubit also does not just disappear into the ether, right? What that means is that if we want to throw away the qubit, we have to use an operation. In this case, I call it discard. So it's also like a linear type, so it consumes the qubit, and then it returns the unit, which is dummy value. So that's a way to say we are discarding the qubit. So for example, maybe in the maybe in the program, we first initialize the qubit, which we call x, and then we use x in a program somewhere, and then in the end, we cannot just forget about x and then do something else, right? We have to explicitly say, oh, we are done with using x. So that's how we say we are done with using x. We just apply the discard function on x, and then we carry on to do some other stuff. Okay, so that's what I mean by qubits are resources. Okay, so I just talked about qubits, and we know qubits are special and they are resources. But of course, with quantum computing, we are not just interested in what a qubit looks like or how do we represent qubit. We are more interested in how do we update the state of the qubit so that it sort of performs some computation. In the end, we get some results, right? So how do we update the state of qubit? Well, we use the so-called unitary operation. So what are unitary operations? Well, I will give you some examples of unitary operations in a moment, but they are sort of some kind of special operation that you can apply on a qubit. And they are special operation. They're special. There are reasons that they are special. Right? One reason is that they are reversible. So what that means is that if we have a qubit in the original state, let's say, as we apply a unitary operation, let's say we get a new state, right? Let's say S1. It's reversible. This operation is reversible in the sense that there is a reverse operation that we can apply to the S prime, so that in the end we can get back to the S that we begin with. So with unitary operation, we can apply this operation, but in some sense we can also unapply this operation to turn the qubit back to its original state. So that's a little weird, right? But that is one of the special property of the unitary operation. Another property of the unitary operations is called linearity. Right? So when we apply the unitary operation to a qubit, for example, so a qubit we know can be represented as this combination, linear combination. So the unitary operation can actually be distributed into each of the components, right? So what that means, so that's basically the math of the unitary operation, but the intuition behind this linearity is that if it's sufficient to know how the unitary operation behaves for 0 and for 1, if we know how the unitary operation acts on the bit 0, and if we also know how the unitary operation acts on bit 1, then we know how the unitary operation will act on a qubit. So if we, yeah, so that's what this linearity means for unitary operation. Okay, so that's a little abstract. So let's look at some actual concrete examples of unitary operation. So the first one I have to solve. 5 minutes. Okay. So I probably just have enough time to talk about the basic of quantum computing. But here is an example of unitary operation, right? It's called Hadamard gate. So people call those basic unitary operation, they call them basic quantum gates. So an example of that is Hadamard gate. Right? What Hadamard gate it does, so we talk about linearity. Right? As long as we know how the Hadamard operation acts on 0 and 1, then we know how it acts on a qubit. So the way it acts on 0 and 1 is sort of similar. It's sort of, it turns a 0 into a linear combination of 0 and 1. And similarly for 1, it also turns it into some linear combination of 0 and 1. So in some sense, this is like how we generate a coin toss, right? So if we have a qubit that is in the state 0, then we apply this Hadamard operation. Then we have a qubit that is in the state of 0 and 1 with equal probability. So this operation is actually self-inverse. If you apply this operation again, you get back to the original state. So that's the fun thing about this Hadamard gate. So we have many other gates that sort of did some thing with 0 and 1, but for the time being, I will not go into the detail of that. But we also have the last thing I just want to briefly mention is CNOR gate. So all these Hadamard gates, phase gate, and T gates, they are operations on a single qubit. But the CNOR gate is an operation that you can apply on 2 qubits. So the CNOR is short for control not gate. So what it does is that it has a control qubit and a target qubit. If the control qubit is in the state 1, then it will perform the negation to the target qubit. If the control qubit is in the state 0, then it does not do anything to the target qubit. So that's why we have this CNOR applied to 0, 0, give us 0, 0, because the control qubit, which is the first bit here, is in the state 0, so it does not do anything to the second qubit. Whereas when the control qubit is in 1, then it will negate the second qubit. So we get 1, 0, we get back 1, 1, and 1, 1, we get 1, 0. So that's like a 2 qubit operation, which is fairly important in building quantum circuits. So related to in the quantum programming language side, we can give those operations, each of those operations a linear type, right? So for example, here Hadamard gate is an operation that consumes the qubit and then produces a new qubit. So that's qubit arrow qubit. And here is the so-called circuit diagram for this Hadamard operation. So it's like a circuit with like a box with input wire from left to right, output wire is on the right. So we have similarly for some other gates, and here is the notation for CNOR gate. So it inputs 2 qubits and then it outputs 2 qubits. So the first bit for first qubit is the control bit, right? So this indicates that if this thing is true, then you apply the negation on the second qubit. Otherwise, it does nothing. Okay, so then the last thing I want to mention is the measurement. So measurement is differ from unitary operations, right? So unitary operations are reversible and it has linearity and all the nice things. But when we measure the qubit, which is we want to know the value of a qubit, we have to use measurement. So the measurement sort of consume the qubit, but then you sort of return the bit as a result. So what it does is that it sort of returns 0 and 1 depending on the amplitude of the complex number, almost, right? So we get 0 with probability like square of the alpha, and we get 1 is probability theta square. So measurement is more like unitary in the sense that it's more reversible. So this operation, once we perform this on the qubit, then the qubit basically is gone. We get the classical bit information. Okay, so that's measurement, and so here are examples of sort of quantum program that one can write that sort of describe certain circuit, right? So let's just quickly look at what this does. So here we have the same. Let's forget this exclamation mark for a moment. It takes a unit, which is like take a dummy input, and then it returns 2 qubits. So this qubits, tensor qubits. So that's the notation for tensor. So what it does is that we initialized a qubit, which we call it A, and then we initialize another qubit, let's call that B, and then we apply the signal. Then we first apply the Hadamard gauge to A, and then we apply a signal gauge to B, and then the result of the Hadamard gauge applied to A. So this program actually corresponds to a quantum circuit, and it looks like, the quantum circuit looks like this, right? So this notation is when we initialize the qubit, and this, right? So that, and then we apply the Hadamard gauge to the variable A, right? So that corresponds to, we stack a Hadamard gauge here, and then we apply a signal gauge with target being B, and then control being H of A, which corresponds to this thing. So that's what this little program will generate a circuit like this. So yeah, that's we have more examples of quantum program that generate circuits like that, but for the time being, I will not go through them all. So we have like so here we have another circuit that does some teleportation. So we have a quantum state going in here, and then it ends up we have the exact same quantum states going out here. This circuit is very interesting, but I don't have time to talk about it. And okay, so I think we are sort of out of time now, but let me conclude my talk by just talking about like a future work or future research possibility. So one topic that I am very interested in is how do we verify the correctness of the quantum program? So what do I mean, right? So that means that if we have a quantum program and another quantum program, they both generate some quantum circuits, and we want to know whether or not the circuits that they generated are the same. So that's one way to understand or to prove. So this is related to how do we prove 2 quantum circuits are equal, right? Or when 2 quantum programs represent the same program, for example. Another thing that I'm interested in is how do we develop tests to ensure the program perform correctly. So of course, with classical program, it's sort of fairly established. You have established tool to test your program, but for quantum program, I don't think this is the case. So I would like to see how we can sort of develop test cases or test suits to test quantum circuit or quantum program. Another topic is how do we sort of compile the high-level program. So here by high-level program, imagine the program that I just showed you. Let's call it high-level quantum program. So how do we compile those high-level quantum programs to like a low-level languages, like so that those low-level languages can be run on actual quantum hardware, right? So there are certain proposals for low-level quantum programming assembly language like thing. They are quantum. So this is by Microsoft. They propose this QIR, quantum intermediate representation, something like that. IBM has this open chasm thing, which is also like another assembly like languages. So I'd be interested in knowing how to compile from the high-level language to those low-level language, and then in the end, ultimately, they can be run on actual quantum computer. So the last thing is, I'm also interested in answering this question. Right? Suppose we have a quantum computer that has 127 qubits. What algorithm can we run on them? Can we use them to do something interesting? So you might wonder why 127 qubits in particular? And the answer is that that's the quantum computer in our department that we have access to by IBM. So that's the reason. Yeah. Anyway, that's my talk. So thank you all.
I think the students' best questions first, but I'll briefly answer some. Is this 127 machine you have access to a real quantum computing machine, or is it a simulated?
According to IBM, they are real. but there's a catch though. The qubits are sort of noisy qubits, meaning that it's actually not quite hard to maintain the state of the qubit. So they are fairly volatile. Like any kind of thing might impact the state of a qubit. Like the room of the temperature, the room temperature might impact the state of qubit. Any kind of movement might impact the state of qubit. So it's very tricky to maintain the qubit in the exact state. That's important. So that is known to be a sort of problem. And so those 127 qubits, they might be noisy in that sometimes they might just have noises in finally.
So one follow-up, one obvious starting point, just not knowing anything about this machine, would be to think of the qubits as registers. And then you could say, okay, I will, do, use a graph coloring approach or something else to do register allocation. So whenever I can, I do operations using the qubits, and when I can't, I spill over and do operations in the classical way. I wonder whether that makes any sense at all.
It might make sense. Except I don't really know the details of how the qubit work in actual quantum hardware.
Okay.
It certainly makes sense in this conceptualized environment. If you don't use the qubit, you just sort of store it somewhere. But not using, so the one thing I sort of learned throughout the year is that doing nothing with the qubit still costs you something.
Oh, okay.
Yeah.
What led you to your interest in this particular area if you don't have the background in physics?
Yeah, one nice thing is that you don't necessarily need to have the background of physics to work in quantum computing or quantum programming languages. So my background is more like a type theory, functional programming in general. But they, as we talk about this resource aspect of qubit, is they sort of present something new, even from the conventional perspective. So that's very interesting to me. So that's why I am interested in looking on this quantum programming language.
So it's something new that is interesting to you?
Yes.
Okay. Just curious, like something hit you in your.
Yeah, I mean this resource aspects of quantum computing.
I have a question regarding the example. Do you mind elaborating more how that process of quantum computing could be much more faster than digital?
Right. So those are more like a theoretical result of quantum algorithm. for example, well, basically the first breakthrough in that area is this algorithm which called Shor's algorithm. It's about how you can use quantum circuits to vector integers. So in that circuit, somehow the circuit size is sort of polynomial with respect to the size of the input, something like that. That sort of provide a very first convincing argument for the fact that if we have a quantum computer, then we should be able to factor integer using Shor's algorithm, which make use of quantum circuits. Whereas factoring integers is still a hard problem using conventional method, I believe. So that's one example where quantum computing can provide advantage. So it's not that quantum computing can always provide advantage for all problems. That's not the case. It's only for certain classes of problems that it has been shown that it has advantage.
And a follow-up question on that was, I was wondering, so you have all these codes and algorithms written in digital computers. Right. And like one point in the future, we would consider going to quantum computers. Would that even be possible to compile all those codes to this quantum computing programming?
It is already possible now, which is the surprising thing. You can actually write a program that sort of generates some quantum circuits, and then you can sort of send the circuits to IBM's or some other company's quantum computer. They will run those circuits for you, and then they will send back the results of the measurements.
Have you done that?
Yes, I did that once, but it's for like a 2-qubit thing. It's fairly simple, but it's possible, which is the great thing.